Please get out your outline and turn to page 5 for section 3. The objectives today, what we're going to be talking about, predicting the shape of a molecule using the VSEPR theory. VSEPR is said VSEPR. The second objective of today is to associate the polarity of molecules with the shapes of molecules and relate the polarity and shape of molecules to the properties of a substance. Now, we have already talked about bond polarity, but realize that we are going to expand it to the polarity of molecules. So why do we even need to talk about the shape? We've been talking about Lewis structures. We know what those diagrams look like for us. Well, Lewis structures are simply two-dimensional pictures, and they don't show the true three-dimensional shape of a molecule. And since shape is what determines the physical and chemical properties, it's important to know what that three-dimensional shape actually looks like instead of the flattened version on paper. As you look, this is what we would draw for a Lewis structure for methane. And notice how flat it looks as compared to the real structure is pyramidal in shape. Using the VSEPR theory, a Lewis structure can be used to predict the shape. Well, what does VSEPR theory stand for? Our simple definition simply says, a theory that predicts some molecular shapes based on the idea that pairs of valence electrons surrounding an atom repel each other. The acronym VSEPR that we're using stands for valence shell electron pair repulsion theory. I'll say that one more time because you might want to write this down. VSEPR stands for valence shell electron pair repulsion theory. Since electrons are negatively charged, that means anytime an electron cloud gets near another electron cloud, they're going to push away from each other, and they're going to push as far as they possibly can. Once they cross the 180-degree angle, however, they're going to be pushing against each other in the opposite direction. So the maximum angle that we could be talking about here is 180 degrees. The shape of a molecule is determined by the structural pairs surrounding the central atom. There are two important points in that statement. The first one is the structural pairs, which simply mean a single, or a double, or a triple bond, or even an unbonded electron pairs. Each one of those represents a structural pair. The second really important thing in this statement is surrounding the central atom. Only the central atom matters when we're trying to predict our shapes. If you look at the page following, page 5 of the outline, you will see it says structural pair geometries for 2 to 4 structural pairs. And that gives us our basic molecular shapes. We have 3 that we're going to deal with, 3 categories in the Chem 1 level. At the Chem 2 level, we have a whole another page of the structural pair geometry. We're only going to talk about 2, 3, and 4 structural pairs. So that gives us linear, trigonal planar, and tetrahedral. We also need to keep in mind that anytime we have unshared pairs, they will occupy more space than the bond does, whether it's a single, double, or triple. An unshared pair balloons and fills up more space. That causes the angles that it's getting close to be reduced from their original distance or angle, and therefore the molecule becomes bent. This practice that you see here, predict the shapes of the following molecules and polyatomic ions. There are just 4 molecules listed here, but this practice will be another video. So you'll have to leave this, and when you finish with the last 2 slides that are here, leave this presentation and look at the one that's labeled practice. So we talked about the idea that molecular shape is important because that determines the chemical and physical properties of a substance. Polarity of a molecule depends on polarity of each bond. and the way the bonds are arranged in space. So we've already talked about the idea of carbon dioxide, carbon being in the center, the green one, and then we have the two oxygens on each side. If you will look back at your table of electronegativities, also in your outline packet, when you look at the table of electronegativities and you look up carbon, you find that it has an electronegativity of 2.5 and oxygen has an electronegativity of 3.5. So when we subtract 3.5, we take 3.5 and subtract 2.5. The difference here is 1, which says that this bond is polar. The bond between this carbon and oxygen is polar. From this carbon to that oxygen is also polar. Notice the symbol that they have included in this picture. We have a positive sign here, and it shows that the electrons are being shifted to the other end. Same thing happens here. Positive sign, electrons being shifted to the other end. Remember that since oxygen has a higher electronegativity, it pulls the electrons toward its end of the molecule. The fact that these are pulled equally from the carbon says that the molecule is also polar. Sorry, it's nonpolar in this case. We'll talk about the one that is polar later. The fact that this is symmetrical, and I could fold it along a dotted line here, and that's a line of symmetry. I could also fold it this way. This is another line of symmetry, and therefore we say that this is nonpolar molecule. The whole molecule is nonpolar, even though this bond is polar as well as this bond is polar. Now let's look at water. We have oxygen in the middle and hydrogen on each of the two ends. Again, the idea, water is made up of hydrogen and oxygen. When we look up the electronegativities, hydrogen is 2.1, oxygen is 3.5. Subtracting those, we get a difference of 1.4. So we know that this bond is very polar, and so is this one. Again, look at our symbol that's been put on the diagram for us. The electrons are shifting toward the oxygen. In fact, we have extra electrons up here, which means that it's slightly negative. If this end of the molecule is slightly negative because the electrons have shifted toward the oxygen, that means that down here on the hydrogens, it's slightly positive. Slightly negative, slightly positive, meaning that I have poles. That means this whole molecule is polar, polar bonds, as well as a polar molecule. We have a line of symmetry here, but there is not a line of symmetry in this direction. If I have only one line of symmetry, the molecule cannot be nonpolar. Remember up here we had a line of symmetry going across as well as going down. Two lines of symmetry usually typifies the fact that it is a nonpolar molecule. Polar bonds that are in exact opposite directions cancel each other, and the molecule is nonpolar. So that's what we were talking about. Exactly, again, a line of symmetry here and a line of symmetry here means that it is nonpolar. Bonds that are at an angle to each other do not cancel each other, and the molecule is polar. Look again, we have all kinds of electrons right here, so this is a negatively charged end of the molecule. Over here, if that's the case, the electrons have shifted in this direction. That means that there is a positive end to this molecule. That means that this molecule is polar. If another water molecule was to get close to this, remember that it has a positive and a negative end also. So that being the case, the positive end would get in here close to these electrons and be attracted, forming a bond. And another water molecule would do that same thing, and another water molecule, and this is the idea of hydrogen bonding. That is one of the reasons why water has such a high melting point and a high boiling point as compared to other molecular substances that hydrogen bonding helps those water molecules to stay close to each other. Now remember, since you're done with this and you have everything filled in on your outline except for the practice problems, you're going to leave this video and go to the practice problem video.